AB Calculus 5.1, day number 2, antiderivatives continued. Take a minute, attempt A, B, and C for example 1, come back and check your work using the power rule. Okay, you're back. Let's check your work. Using the power rule, we would see that 3x to the 5th over 5 plus c would be the antiderivative of 3x to the 4th with respect to x. You could find the derivative of your antiderivative and show, again, verifying that 3x to the 4th is the derivative of 3x to the 5th over 5 plus c. For part B, you should get x plus c. For part C, maybe you struggled with this, but we're going to have the natural log of the absolute value of x plus c. We won't talk about why the absolute value is used here, but use it, okay? If you have a question about that, you can ask your teacher, or we can talk about that further based on circumstance. Okay, so the antiderivatives that I'd like you to memorize here are going to be each of the 6. So I'd like you to fill those in and come back and check your work with mine. Okay, you can check your work with those 6. Those are some standard antiderivatives that you're going to want to be able to work with. Okay, and recall at a pretty quick rate. All right, so take a look at example 2. We're going to find and determine the following indefinite integrals. Now, there's a special rule called, well, not a rule, but a technique called integration by substitution. And we talked about this briefly in the first lesson, but we don't know how to use integration by substitution technically yet. And integration by substitution is sometimes referred to as a u substitution, because the variable that we use is the variable u. Now, I'm not going to use that technique yet, but in doing both of these problems, you will be using this u substitution or integration by substitution method. So think through A and B, and then come back and I'll walk through these. Okay, so the temptation for both of these is to say that this would be e to the 3x plus c. But the derivative of e to the 3x plus c, right, if I took the derivative of e to the 3x, x plus c would equal 3e to the 3x. Now I need to do something with this 3 to get rid of it, because as you can see, the original function did not include that 3. So what I do is I throw 1/3 on there. So as I look at part B, a general form of the same thing, or of a similar problem, what I would do is I'd multiply by 1 over that coefficient of the exponent of e to the power of ax. And when I take the derivative of that, you'll see that the a in ax reduces with the 1 over a. And of course the c is gone bye-bye when you take the derivative. Okay, so this is a form of this idea of integration by substitution, which of course we'll cover in later sections. All right, let's continue. Okay, recall that this problem, the first problem we see up here, the antiderivative of 3x squared dx is x to the 3rd plus c. What this did was this found a general solution. Right, a general solution. And that general solution created a family, right, a family of functions such that their derivatives were all equal to 3x squared. Right, so what created the family? Well, this potential shift, vertical shift. Now, what if we wanted a particular solution? What if we wanted to know a very specific function, right? Instead of just generalizing in terms of c, we could find the particular solution that said that we could say, I don't know, passes through 1, 4. So, right, we could have all of these functions. We could have x cubed plus 0. We can have x cubed plus 1. We could have many others. Right? We want to know the particular solution that passes through the point 1, 4. So let's try to find the solution so that f of 1 is 4. So when we integrate, of course, we get this idea here. So I'm saying that my function is y equals x cubed plus c. If that function is to satisfy the ordered pair 1, 4, then that means that 4 should equal 1 cubed plus c. Now I can find the c value, which then finds me the particular solution to this antiderivative. Okay, so it looks like c would equal 3, and therefore the solution that passes through 1, 4 would be y equals x cubed plus 3. Okay, so let's look at example 3. We got two examples. We're going to find the antiderivative capital F that satisfies the given condition. So we are going to find the particular solution to the equation given, or to the situation given. Okay, so if we want to know what big F of t is, of course we'd take the antiderivative of secant squared of t with respect to the independent variable t, which is going to be tangent of t plus c. So what I'm saying is that my family of functions can be written as the tangent of t plus c. Now I want it to satisfy this condition, pi over 4 comma 1. And thus, if I plug a 1 in for y and a pi over 4 for t, you'll see that the tangent of pi over 4, yeah, the trig's not going away, so don't wish it away because it's not happening. We see that c equals 0. Thus, the particular solution, or the function, I guess I could call it big F in a moment, that would satisfy an input of pi over 4 equaling an output of 1 would just be tangent of t. Thus, let me put this in proper notation. Big F of t is tangent of t. All right, let's move on to part B here. And let's start again like we did in the previous problem by taking the integral of f of x, which is x squared minus 2x, with respect to x. That'll be x cubed over 3 minus x squared plus c. Okay, now let's take that function, we'll call it y for the time being, and let's go ahead and determine the value for c such that 1 comma 1/3 satisfies this equation. Okay, so 1/3 is equal to 1 cubed over 3 minus 1 squared, which is 1. Okay, so that would mean that 1/3 is equal to 2/3, negative 2/3 plus c. Thus, c would equal 1. Therefore, f, big F of x, that is, will equal x cubed over 3 minus x squared plus 1. All right, let's continue with some more examples. Okay, a bit of a challenge, but I think you're up for it. If you take the antiderivative of v of t, and let's refer to v of t as velocity, right? The antiderivative of velocity would be position function plus c. The antiderivative of acceleration would be velocity plus some constant of integration. So let's take a look at example 5. Example 5 says v of t equals the following, and s of 0, or the initial position, is 0. Find the position function. Now this is a particular position function, not a family of functions. So we're going to use our skills that we just built on the last slide. Okay, so the integral of v of t, and you are allowed to shorthand this and then just do the calculation in your head. Okay, that would be 6t cubed over 3, we can simplify in a moment, plus 4t squared over 2 minus 10t plus c. All right, now this new polynomial equation is the family of functions for x of t. But since we have an initial condition, actually I'll do a little simplifying here. Let's make this 2t cubed plus 2t squared minus 10t plus c. Since x of 0, or s of 0, these two are synonymous with each other, equals 0, then each of these, clearly if I plugged in a 0 for each of these t values, I would get 0 plus 0 plus 0 plus c. Therefore, c equals 0, and thus our particular position function would equal 2t cubed plus 2t squared minus 10t. Okay, part B, v of t equals 1 over t, and s of 1 equals 4. Find the position function. Again, the antiderivative or integral of v of t will equal the natural log of t plus c. So I could say that s of t or x of t is equal to the natural log of the absolute value of t plus c. Now if the initial position is 4 when t equals 1, then we know the natural log of 1 is 0, therefore 4 would equal c. Thus the particular position function for this scenario would just be the natural log of t plus 4. All right, let's look at part C. A of t is cosine 2t, v of 0 is 1, and s of 0 is 0. So we're going to start with a of t. I'm going to take the antiderivative, or the integral of a of t with respect to t. Okay, so when we do this, we want to consider, I'm actually going to take 2 out, right? The antiderivative of cosine of t is sine t, so I'm just going to distribute that back in. So I get 2 sine of t plus c. Now this would provide us a family of velocity functions whose acceleration is 2 cosine of t. Now I want to find the velocity function that satisfies v of 0 equal to 1. So when I plug in a 0 for t, I get out a 1 for the velocity. Well, sine of 0 is 0, therefore c has to equal 1. Therefore, velocity will equal 2 sine of t plus 1 for this given scenario. Now, as we know, the integral of v of t dt is equal to the position function plus c. Thus, v of t, its integral, in this case, would be negative 2 cosine of t plus c. Right? I took the antiderivative of the following. Now consider that the derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. The antiderivative of 1 is t, and of course we got to add our condition. Okay, so this is our position family function. Okay, and we have to satisfy 0, 0. Well, cosine at 0 is 1. Therefore, 0 is equal to negative 2 plus c. Therefore, c equals 2. Okay, thus, the position function, particular to this situation, would be negative 2 cosine of t plus 2. So we've got our position function, we had our velocity function, and of course, we had our acceleration function. There you have it. I believe this is what we were looking for in particular. That would be our position function in this situation. All right, let's continue with some more examples. All right, AP style questions, love them. Let's get going on them, both non-calculator. Particle moves along the x-axis with velocity given as follows. For t greater than or equal to 0, if the particle is at position x equals 2 when t equals 0. So I'm going to say x of 0 equals 2. What is the position of the particle at t equals 1? So I want to know x of 1. Okay, so let's set this up. The integral of velocity, of course, we know is position. So the integral of this would be t cubed plus 3t squared plus c. Okay, you could check those by finding the derivative of that, showing it equals v of t. All right, so x of t, generally speaking, would be this. Now, our initial position is 2. Oops, that should be a 0 squared plus c. So it looks like c equals 2. Okay, thus, x of t is t cubed plus 3t squared plus 2. So x of 1, if I plug a 1 in here, I get 1 cubed plus 3 times 1 squared, which is 3, plus a 2. Looks like our position at time t equals 1 is going to equal 6. All right, let's look at number 14 from 1998. Particle moves along the x-axis, so its position is given by the following. For what value of t is the velocity of the particle 0? Okay, now change your mindset for a moment. X of t is x squared, t squared, minus 6t. Common mistake, guys. Try to keep your independent variable along here in mindset. I like to think of x of t. Sometimes I think of one as the independent variable instead of the other. So x prime of t is v of t, and x prime of t, of course, is 2t minus 6. Now I took a derivative, right? I operated using the derivative, not the antiderivative, so don't get confused. We're not even working the antiderivative at all. Now it asks for what value t of t is the velocity of the particle equal to 0. So v of t equals 0 when 2t minus 6 equals 0. Therefore, when t equals 3, v of t equals 0. Or in other words, v of 3 is equal to 0. So the particle's at rest at time t equals 3. All right, let's continue with a couple more examples. All right, 1997, problem number 87, calculator allowed. Okay, let's go ahead and get into this. It looks like it gives us a of t, and it gives us an initial velocity. So it tells us our initial velocity is negative 2. So as we know, the integral of a of t with respect to t is going to end up equaling our velocity. So our velocity in this case will equal t squared over 2 minus cosine of t plus c. Be careful with your signs there. So I'm going to say a general equation for the velocity function would be t squared over 2 minus cosine of t plus c. Now using this condition that v of 0 equals negative 2, plug a negative 2 in here and a 0 in for t. Cosine at 0 is 1. Therefore, negative 2 is equal to negative 1 plus c. Okay, so it looks like negative 1 is equal to c. Thus, our velocity, particular to this situation, would be as follows. Now what I'm going to do is I'm going to graph this using my calculator. I mean, if this were a polynomial equation, I could potentially solve without, but I'm going to graph it using my calculator on an interval that, I'm going to graph it from 0 up to, let's go to 4, just based on the max value I see and the minimum value I see here. And what I'm looking for is what t value, okay, what t value gives me a velocity of 0. So I'm looking to see where my velocity graph crosses that t-axis. Okay, so I took my graph, or my value, my function for v of t. I plugged it in for y1. So in for y1, I plugged v of t. And out came this thing, right? This graph, this blue graph here. So this is v of t. I notice, obviously, that there's a point of intersection here. So I use my, my calculator's ability to trace, right? So I press second trace, use the 0 option. And it asked for a left bound, then a right bound, and then a guess. And it came out with a value, right, where v of 1.4781703 is equal to 0. So the t value that I'm looking for is 1.478. Now to 3 decimal places, that's just 1.48. So it looks like our answer to this question would be B. All right, guys, that's it for 5.1, day number 2. See you in the next video.